On the night of January 31st, 1953, a combination of high tide and hurricane-force winds created a wall of water that smashed into the Netherlands, breaking through dikes in hundreds of locations and flooding over 2,000 square kilometers of land. By the time the water finally receded, 1,835 people were dead. More than 70,000 had been evacuated, and tens of thousands of homes were destroyed. In the village of Oude Tong, a 15-year-old girl named Ali van der Wal climbed onto her roof with her younger brother as water rose past their windows. Rescue boats did not arrive until the next morning. By then, her brother was dead from hypothermia. Ali survived by wrapping herself in a wet carpet. She was one of thousands with similar stories that night. An entire country woke up to the realization that the sea could kill them at any moment, and their old defenses were not strong enough to stop it. Within weeks, the government launched the Delta Works, a plan to build a system of barriers so large and so sophisticated that they could physically close off the ocean when it got too dangerous. The centerpiece of that system is a storm surge barrier so enormous that each of its two moving gates weighs 6,800 tons and can swing shut across a 360-meter shipping channel in less than 2.5 hours. When it closes, Rotterdam and millions of people behind it are protected. When it stays open, one of the busiest ports in the world keeps running, and the decision to close it is made by a computer, not a person, because there is no time for meetings when the water is already rising. The Dutch have been fighting the sea for centuries. More than a quarter of the country sits below sea level, and without constant pumping and barriers, large parts of it would simply disappear underwater. For most of history, the defense strategy was simple. Build dikes, make them high, make them thick, and hope they hold. The 1953 flood proved that hope was not enough. The storm hit at night during a spring tide, when water levels were already elevated. Winds reached 160 kilometers per hour, pushing a surge several meters high directly into the weakest points of the coastal defenses. Dikes that had stood for generations cracked, crumbled, or were overtopped within minutes. Water poured into low-lying areas faster than anyone could react. Entire islands were submerged. Villages disappeared. Families drowned in their homes. Rescue crews spent days pulling survivors off rooftops and out of attics, while bodies floated past in the freezing water. The scale of the disaster forced an immediate decision. The country could either abandon large parts of its coastline and move millions of people inland, or it could build defenses strong enough to survive storms that might only happen once every few centuries. The Dutch chose to fight. In February 1953, just 2 weeks after the flood, the government formed the Delta Committee and gave it a mandate to design a solution that would prevent this from ever happening again. The result was the Delta Plan, a decades-long construction program that would reshape the entire southwestern coast. Engineers proposed shortening the coastline by building massive barriers across river mouths and estuaries, reducing the length of vulnerable dikes by hundreds of kilometers. Some barriers would be permanent dams that closed off tidal inlets entirely. Others would be movable gates that could open to allow shipping and tidal flow under normal conditions, but slam shut when a storm surge was detected. The Maeslantkering, completed in 1986, became the largest storm surge barrier in the world at the time. It spans 9 kilometers across the Eastern Scheldt estuary and consists of 65 concrete piers, each weighing up to 18,000 tons, supporting 62 steel gates. The gates are lifted by hydraulic systems when water levels rise above safe thresholds. During normal conditions, the gates remain open, allowing tides to flow in and out and preserving the ecosystem. When a storm approaches, operators lower the gates, and the barrier becomes a solid wall of steel and concrete, separating the inland waterways from the ocean. Construction took nearly a decade and required some of the heaviest engineering equipment ever used in a coastal project. Each pier had to be floated into position, sunk onto a prepared foundation, and anchored against currents strong enough to move ships. But the Maeslantkering had a limitation. It protected the Eastern Scheldt, but it did not protect Rotterdam. The city sits at the mouth of the Rhine, one of Europe's busiest shipping routes. Blocking that waterway with a permanent dam would cripple the port and destroy the local economy. Engineers needed a barrier that could stay open 99% of the time, allow the largest cargo ships in the world to pass through without restriction, and still close fast enough to stop a storm surge when needed. That barrier would become the Maeslantkering, and it would push the limits of what was physically possible to build. The design challenge was brutal. The barrier had to span 360 meters of open water in a channel that handles more than 30,000 ships per year. It could not have a center support or pier in the middle of the waterway because that would block navigation. That meant the two gates had to be cantilevered structures, supported only at their hinges on opposite banks, capable of swinging out and meeting in the center of the channel. Each gate is a curved steel truss 210 meters long, shaped like a segment of a sphere. When open, the gates rest in dry docks on either side of the river. When a storm is coming, they swing out on massive ball joints, float across the waterway, and lock together in the center. Once locked, valves open and seawater floods the hollow compartments inside each gate, adding weight and sinking them down onto a concrete sill on the riverbed. At that point, the barrier becomes a solid wall holding back the ocean. The ball joints that allow the gates to rotate are among the largest ever made. Each joint is 10 meters in diameter and weighs 680 tons. They were manufactured in the Czech Republic at Škoda Works, the same facility known for heavy industrial equipment and locomotives. The joint acts like a human shoulder, allowing the gate to move freely in multiple directions, while transferring all the force exerted by the water onto a single pivot point anchored deep into the riverbank. During a storm, when the sea is pushing against the closed gates with millions of tons of pressure, every bit of that force is channeled through the ball joint and into the foundation. If the joint fails, the gate tears loose and Rotterdam floods. There is no backup, no second chance. The joint either holds or the city drowns. The construction process was a logistical nightmare. The gates are so large that they could not be built in place. Instead, they were assembled in sections in a nearby fabrication yard, then floated to the site on barges. Each gate weighs 6,800 tons and is held upright by a steel truss framework that is 237 meters long. Workers had to align the gate with its ball joint to within millimeters, a task made harder by wind, current, and the fact that they were working on floating platforms in an active shipping channel. Once installed, the gates had to be tested repeatedly to make sure they could open, close, and seal properly under different conditions. Engineers ran hundreds of simulations and physical tests before they were confident the system would work when it mattered. The barrier is fully automated. A centralized computer system called BOS continuously monitors weather forecasts, tidal data, wind speed, and water levels across the North Sea. When the system calculates that a storm surge will push water levels above a critical threshold, it triggers the closing sequence without waiting for human approval. The reason is simple: there is not enough time. A surge can develop faster than people can react, and by the time someone notices the water is too high, it may already be too late to close the gates. Automation removes hesitation and ensures the barrier responds immediately. No meetings, no phone calls, no debates. The computer detects the threat and the gates move. When the computer issues a close command, alarms sound and warning lights activate along the waterway. Ships in the area are notified and traffic is halted. The two gates begin their rotation, swinging out from their dry docks and moving toward the center of the channel. The process takes about 2.5 hours under controlled conditions. As the gates approach each other, they slow down and use positioning sensors to align perfectly. Once they lock together, the flooding valves open and seawater pours into the hollow chambers inside each gate. As the chambers fill, the gates grow heavier and sink down until they rest on the concrete sill at the bottom of the river. At that point, the barrier is fully closed and the ocean is physically blocked. The forces acting on the closed gates are immense. During a major storm, the difference in water level between the seaside and the inland side can exceed 3 meters. That difference translates into millions of tons of pressure, trying to push the gates open or tear them off their hinges. The steel trusses are designed to handle these loads by distributing the force along their entire length and channeling it back to the ball joint. Engineers calculated the maximum storm the barrier would ever face by looking at historical data and projecting the worst-case scenario that might happen once every 10,000 years. The Maeslantkering was built to survive that storm, with a safety margin built in. But no one knows if the calculations are correct until the storm actually arrives. The barrier has been tested multiple times since it was completed in 1997. But for most of its life, it remained open. Storm surges strong enough to trigger a closure are rare. In December 2023, Storm Pia hit the North Sea and generated a surge more than 3 meters above normal high tide levels. For the first time since the barrier became operational, the computer system detected the threat and initiated an actual emergency closure during a real storm. The gates swung shut, the chambers flooded, and the barrier sealed off the waterway. At the same time, other barriers across the Delta Works system also closed, creating a unified defense line along the entire Dutch coast. Engineers watched from the control room as sensors transmitted data on gate position, water pressure, and structural integrity. Everything held. The storm passed, the surge receded, and the gates reopened. Rotterdam did not flood. The system worked exactly as it was designed to, but the engineers knew they had been lucky. Any mechanical failure, any software glitch, any miscalculation in the storm forecast, and the outcome could have been catastrophic. But the Maeslantkering was not built for the storms of today. It was built for the storms of the next century. Climate change is raising sea levels and increasing the frequency of extreme weather events. A barrier designed to close once every 10 years may soon need to close multiple times per year. Engineers are already studying whether the gates can handle the increased workload and whether the mechanical systems will wear out faster than expected. Each closure puts stress on the hinges, seals, and control systems. Each time the gates sink and rise, the risk of a malfunction increases. And if a closure is needed but the system fails to respond, the consequences are not theoretical. Millions of people live and work in areas that will flood if the barrier does not close. Hospitals, schools, power plants, data centers, and critical infrastructure all sit behind that line of defense. One failure means one disaster. There is also the problem of what happens after a closure. Once the gates are sealed and the storm surge is blocked, the water on the inland side has nowhere to go. Rain that falls upstream continues to flow down the rivers toward the sea, but it cannot pass through the closed barrier. That means water begins to back up behind the gates, raising river levels and threatening inland flooding from the opposite direction. To prevent this, the Dutch have built a network of pumping stations and overflow channels that can divert excess water away from populated areas until the barrier reopens. But this system has limits. If a storm lasts too long or dumps too much rain, even the pumps may not be able to keep up. The barrier protects against the sea, but it creates a new problem on land. The Dutch also built other barriers as part of the Delta Works. The Maeslantkering and the Hollandse IJssel barrier protect smaller waterways leading into Rotterdam. Together with the Maeslantkering, they form a layered defense that can isolate the city from the sea during a major storm. All of these barriers are designed to work in coordination, with the largest outer barriers taking the first hit, and the smaller inner barriers serving as backups. This redundancy is critical because a failure at any point in the system leaves entire regions exposed. If the Maeslantkering fails, the smaller barriers downstream will be overwhelmed within hours. The cost of building the Maeslantkering was approximately 450 million euros, and the total Delta Works program cost billions more. That is an enormous investment for a system that spends most of its time doing nothing. But the logic is simple. The barrier only has to work once to justify its existence. A single prevented flood saves billions in damage, thousands of lives, and the entire economic engine of one of Europe's largest ports. The 1953 disaster proved that the cost of not building these defenses is far higher than the cost of building them. The Maeslantkering is not just a piece of infrastructure. It is a statement. It says that a country can choose to fight the ocean instead of retreating from it. It says that engineering can solve problems that seem impossible if you are willing to invest the time, money, and expertise required. And it says that survival sometimes depends on building things so large and so complex that they only make sense when you consider what happens if they are not there. The barrier will not last forever. Engineers estimate it has a lifespan of around 200 years if maintained properly. After that, it will need to be replaced or completely rebuilt. By then, sea levels may have risen so much that a new generation of barriers will be required, possibly even larger and more sophisticated than what exists today. The fight against the ocean is not a problem that gets solved once. It is a permanent commitment that every generation has to renew. For now, the Maeslantkering sits quietly in its dry docks, waiting. Most of the time, ships pass by without noticing it. Tourists visit and take pictures. Engineers run diagnostics and perform maintenance. But they know the truth. Climate change is making surges stronger and more frequent. A barrier designed to close once every 10 years may soon need to close every year. And every time it closes, there is a chance it will not open again. The ocean does not forgive mechanical failures. The Dutch have bet millions of lives on 2 gates and a computer. If the gates fail to close when the next surge comes, Rotterdam floods. If they close but fail to hold, Rotterdam floods. If they hold but fail to reopen, the rivers back up and Rotterdam floods from behind. There is no margin for error. The machine works, or the city drowns. That is the deal the Dutch made with the sea.